Welcome to the solutions to the Regents Physics Electromagnetism problem set, problems numbers 3, 5, and 7. Number 3, in what direction in relation to a magnetic field would you run a current carrying wire so that the force on it resulting from the field is minimized or even made to be zero? Well, hopefully from our lesson you've learned that perpendicular is the key word, that the maximum force experienced by any charge carrying situation, whether it be a current carrying wire or a charge moving in an existing magnetic field, that to maximize that force you would move it perpendicular to the field. So to minimize it or even make it to be zero, you would want to have the wire orientated parallel to the magnetic field itself. In this case, there would be no force experienced at all on the current carrying wire. Number 5. A beam of protons is moving from the back of the room to the front of the room. It is deflected upward by a magnetic field. What is the direction of the magnetic field causing the deflection? All right, so protons is key here. And that indicates to us positive charges. So it tells us we're going to use our right hand for the right hand rule here. We're also told that it's moving from the back to the front of the room. Okay, so that means our positive charges have a velocity that's into the page, or in the z-plane here. We're also told that they're deflected upward. That means they're forced due to the magnetic field upward. So FB is upward, our velocity is into the page. Well, our force lies in the y-plane, our velocity lies in the z-plane. That means our magnetic field itself has to be directed in the x-plane. Great technique to help you eliminate down to 2 possible directions. Using the FBI hand rule, we take our thumb and point it into the page. Our middle finger that represents force is pointed upward. And when we have our thumb pointed in and our middle finger pointed up, we have our index finger pointed to the left. So our B field is from right to left. And this indicates that the north pole creating the magnetism must be on the right side of the room, and the south pole creating the magnetism has to be on the left side of the room, so that the magnetic field goes away from the north towards the south from right to left. If you don't understand this, make sure you ask in class tomorrow. Lastly, number 7, a wire 1.50 meters long carrying a current of 10 amps is at right angles to a uniform magnetic field. The force acting on the wire is 0.600 newtons. What is the strength of the magnetic field itself? Well, the equation to calculate the force on a current carrying wire in an existing magnetic field is F equals BIL. In this equation they provided F, they provided I, and they provided L, and they're asking us for B. We go ahead and we substitute and calculate, and we should get a magnetic field strength of 0.04 Tesla. All right, that'll do it on problems 3, 5, and 7. More to come in class tomorrow as we tackle problem 11 together in class tomorrow.